will be always 1 or 0. So what is the requirement for a gate, and why we need this gate? That things implementations will be explained in lab. So for just a simple example, I can tell you, like for example, like that things will be studied in later. So if you want to set a pin for a anything, like it's a 4-digit pin, okay, like in your suitcase you will have a 3-digit pin, right? So similarly, like we can have a, like if it's for example a 4-digit pin is there, that means we can give a ABCD like 4 inputs. So how these gates, different gates are in like combination gates, it's separate. Combination gates comes means, so that specific input only, like we will get an output. So in the KMA production and all, we will discuss in later in the class. So these gates have many applications. Okay. So for example, if you come consider any processing in computer, this is based on the gates, that is ones and zeros. Okay. So we and so then I think in this first lab after that, someone asked why we have 4 gates in a single IC, and what's the difference between gate and IC. So IC is different from a gate. Gate is like what is that? Is a theoretic thing. Like it is not like IC. Okay, so an IC could have many gates, or some ICs will be having many other things also, like memory. Anything could be there on an IC. Okay, so for lab experiment, ICs like 7408, those things will have gates, like 1 or 2, 3 gates will be there. Okay, so a few of the different gate are discussed here. So small scale integration SSI, that is having less than 12 gates per chip. So that is called SSI. So then it came the MSI, which have greater than around 100. Then it was around 1,000. And now we have like millions and billions of gates in a single IC. Okay, that's called like our processor. So it have like many, I think around 1.6 billion transistors are there on a single IC of an i5 processor and i5 i7 processor. Okay. I hope that I'm audible now. Okay, so we'll just discuss the basic gates. So this one is the NOT gate. It is like these all things already we have discussed, but I will just have a discussion once more. This is a simple NOT gate where we give an input 0, we will get an output as 1, and vice versa. Okay, and this is the symbol of the NOT gates. This call roll number 63. Yeah, am I audible now or okay? Please don't keep on chatting if it's not necessary. Like it's distracting me. Okay, it's fine. So like this is a single NOT gate. So that is the triangle with a bubble. That is the symbol of the NOT gate. Okay. So that circuit is nothing like if we have a battery, or this is the equivalent circuit where we have a battery and a switch is connected in parallel to the lamp. So if that switch is connected means the lamp won't light. Why? Because that the I hope you know the electronics part. Okay, because the current will pass. You first year you might have studied. The current will pass through the uh, pass through the path which have the least resistance. So if I have a switch is connected in parallel to a lamp, and if that switch is closed, it means the current will take that path and the lamp won't get the current and the lamp won't be light. Okay, that is the equivalent of a NOT gate. So next one is an OR gate. So okay, I forgot to say one more thing. The NOT gate will have only single input and single output. So whatever is the input, that will be inverted. Now coming to OR gate we have 2 inputs and 1 output. So a OR gate is equivalent of the sum that we had studied earlier. So okay, so it is used for logical addition. So if the sum is if 0, if the inputs are given as 0 and 0, we will get an output 0. And the as follows, like 0 1 means output is 1, 1 0 means output is 1, and 1 1 also the output will be 1. Okay, to memorize and understand the circuit, the simple circuit you can see. In that circuit, like 2 switches are there and 1 lamp is there. If any of the switch is on, like closed, if any of the switch is closed means the lamp will light up. If 2 switches are on also, the lamp will light. But if both are off or the close open situation means the lamp will not be lighted up. Okay. Now, and this is the AND gate. AND gate is at the both condition. This condition, like You may be already knowing this condition, but I'm explaining once more. Or and condition is the case where both condition has to be satisfied. Both A and B has to be satisfied. Then only you will get an output. So in that truth table, you can see that the output is one only in one case. That is when both inputs are one. Okay. So here also in the equivalent circuit, you can see that the gates are in series. So if any of the switch is open, means the light won't be on. Both needs to be in the closed state. And one thing is that OR and NOT gates are called basic gates because any logical expression can be realized by using and or and NOT gates. Okay, that's why they are called as basic gates. So we have basic gates and we have universal gates. Okay. So what is my universal gates are two gates. NOR and NAND are called universal gates. So can anyone say why NOR and NAND are called universal gates?
We can
Like
build
any
any
kind
other
of
gate
gate
with
can
those
be,
two gates.
yes, sir.
Yes. Any gate can be implemented using NOR and NAND gates, right? Okay. So when comes to NOR gate is just but nothing but the inversion of an OR gate. So whatever be the truth table of OR gate, it is just inverted. That is the truth table of NOR gate. You can see that when in OR gate, what we will see. So whatever be like, we will have an output one. Like we have output zero only in one case when both gates are zero. When the rest all three cases, we have the output as one. But when it comes to NOR gate, we have an output of one only in one case. That is when we have both input as zero. But in the case, the all other three cases, we will have an output of zero. Okay, that's clear. I'm talking about the truth table where A and B. Okay, and this is the NAND gate. NAND gate is just the complement of AND gate. So in an AND gate, what we have is that whatever like only in one case when both inputs are one, we will have an output of zero. All the other three cases, we will have an output of one. But when it came to AND gate, it was just the opposite. We had output of one only when both inputs were one. Now it comes to exclusive OR gate. So it is different from AND gate and an OR and all those things. So what is the difference is that in an exclusive OR gate, the output will be only one when we have a difference in the inputs. That is if A and B are different, then the output will be one. But if A and B are same, then the output will be zero. That is an exclusive OR gate. Okay. And the expression for that same is y equal to A bar B plus A B bar. Okay. Can you just please try this truth table and verify the truth table using the expression? Please verify the truth table using that expression. Do it in your notebook.
Yes, sir, it satisfies, sir.
Okay. Now only 43 are present in the class. Okay, I will note down the number of absentees. The class rep can send me the number of absentees later on. Okay, so this is an exclusive NOR gate. So here it is just the bar of exclusive OR gate. So it is exclusive NOR gate. We will get an inverted output of the exclusive OR gate. So here we what we can see is that the output will be 1 when both inputs are same. Okay. The output what the output we are getting is both inputs are same. Okay. And the expression is A dot B plus A bar dot B bar. Please verify this one also.
Yes, sir, it's verified.
Satisfying, sir.
Okay. So the next exercise is to construct AND gate, OR gate, NOR gate, NOT gate, XOR and XNOR. All these gates that we have discussed using NAND gate. You can do them right away, and I will be sending a Google Sheet after the class to so that I can verify what we have done today in the class. You can send the scanned copy of the notes to the Google Sheet. Okay, I will send a Google Sheet link. You can upload your class note, whatever we have written today. Okay. So next exercise is to construct AND or NOR and NOT gate, also XOR and NOR gates by NAND gate using a NAND gate.
Sir,
Yes.
sir, we should do this, sir. I couldn't hear.
Yes, yes. As of now, you can do it now itself.
Okay.
Sir,
Yes.
is the construction should consist of only NAND gate, sir?
Yes.
Only
Yes.
NAND gate.
Only NAND gates. Use
Or we can use NOT gate also.
no, using NAND gate alone. NAND. Only NAND gates.
Okay.
But like we have to design a circuit keeping NAND gates, sir.
You make an AND gate using NAND gate alone.
So can you please show an examples or like any of the gates how to do?
Yes, 1 second. I will
So
make
can
one.
we use the gate itself in the circuit?
Didn't you understand that? You use NAND gate to create an AND gate. So you can
Oh,
use
okay, sir. Okay,
any
sir.
number of AND gates, but try to use minimum number.
Okay, sir.
So to create an AND gate using NAND, you just need 2 NAND gates. You can use more, it's up to you, but try to use just 2.
Sir, and gate, I created, sir.
Okay, then you can go further. Like you have to create everything, or, nor, not.
Yeah, okay, sir.
Okay. So, hello. I guess listening.
Yes, sir.
Yes, this is an
Yes,
implementation.
sir.
Yes, it took some time because I implemented in multi-sims to show it to you easily. So this is an implementation using a NAND gate, two NAND gates to use an AND gate. Okay. So in this case, it is 0, 0, it won't light up. Okay. Then 0, 1, 0. Okay, again it won't light up. Now we'll see 1, 1. I hope it lights up. Yes. Is it visible? Hello? Am I audible?
Sir.
So you can get an output of NAND and sorry AND gate using NAND. Where if you give 1, 1 only, the LED will get light up. Okay. So similarly, you can make and or nor and all the other gates. You want me to demonstrate any other gates? No need to do it in multi-sim. Like if you can draw it in your notebook, you can if you want you can later verify in your multi-sim. That's up to you. Okay. Is it done completely? Have anyone done till XNOR? You have to understand what's the truth table is. Then you can easily like if you want me to show any specific gate, you can ask me to. I will show that gate. I hope that you remember all the truth tables, like especially and or and all those things you will be remembering already. You may be not remembering exclusive or.
Sir, three NAND gates are sir for our lesson to itself.
For which one?
OR gate.
Yes. For OR gate, you require three NAND gates. Yes, correct.
Okay, sir.
Okay, I will keep this chart on so that you will be. So if you remember that order, not and or XOR, XNOR, then it will be easy. 1, 2, 3, 4, 5, like that you can. So if this one is done, we can do the next exercise. That is with the NOR gate. Same implementation with NOR gate. So for NOR gate, for a NOT, you just need one. AND gate, you need 3. OR gate, you need 2. XOR, you need 5. XNOR, you need 4. And for a NOR, you just need 1. And a NAND gate, you need 4. While you are doing these examples, I will take the attendance as well. Rule number 1. Rule number 1. 2.
Yes, sir.
3. Rule number 4.
Present, sir.
5. 6.
Present, sir.
7.
Present, sir.
8. 9. 10.
Present, sir.
11.
Present, sir.
13. 13. 14. 14. 15.
Present, sir.
15%.
16.
16 present, sir.
18. 18. 19.
Present, sir.
But 17 is present. 17.
17 is not present, sir.
And 18 is also not present, right? 18. No, okay. 20.
Present, sir.
21. Sorry, 23.
Present, sir.
21. 24.
Present, sir.
25.
Present, sir.
26.
Present, sir.
27.
Present, sir.
28.
Present, sir.
29. 29.
Absent, sir.
30. 30. 32.
Present, sir.
33. 33. 34.
Present,
34.
sir.
35.
Present, sir.
36.
Present, sir.
37.
Present, sir.
39.
Present, sir.
40. 40. 41.
Present, sir.
43,
Present, sir.
44,
Present, sir.
45, 45, 46,
Present, sir.
47,
41 here, sir.
Present, sir. 47 present.
48,
Present, sir. 48 present.
49,
Present, sir.
51,
Present, sir.
52,
Present, sir.
53,
Present, sir.
55,
Present, sir.
54%, sir.
56, 56, 57, 58,
Present, sir.
59,
Present, sir.
60,
Present, sir.
61,
Present, sir.
62,
Present, sir.
63,
Present, sir.
64.
Present, sir.
So this to conclude, like you can do this exercise in your notebook, and this is the number of gates required, number of NAND required for all the logic gates, and number of nodes required for all the logic gates. Now we will have two more examples to implement XYZ with minimum number of 2 input NAND gates required. So you can verify that, and to implement AB plus CD, minimum number of 2 input NAND gates required. So you can try to these examples. I will be sending this slide to the class rep and draw the logical circuit using basic gates and generate the truth table of the given logical expression. Okay, so you can do this, all this, for example, this construction of all the basic gates using NAND, NOR, and these 3 examples. Okay, I will email the slides right away. Kindly do this by evening, and we'll see. Okay. Any doubts? Any doubts?
Sir, by what time, sir?
Maybe by some 5 o'clock. I will send the Google sheet.
Okay, sir.
Google form.
Sir, and also you didn't call some students.
I
54, 38.
had called everyone. 54 is called.
You didn't call, sir.
54.
Sir,
It's marked
41, sir.
present.
You called, but I did not respond as I was on my mic. I accidentally hit this disconnect button, sir. So I joined again, and you went to 45, sir. By the time I rejoined.
Okay. That you can anyway. That's anyway. 44 were 40. Please. 43 was
41.
only present in the class totally. So the class rep can again send me the list of absentees. Okay. Kindly contact the class rep and he will mail me. Already he have mailed me the last 2 classes. I am taking it as a backup. If that's not matching with this means I can take that. Okay. Okay, then we will meet at 2:30 for the lab session. Okay. Anybody is still having issues with multisim? Anyone?
Sir, we can do that this in sir.
You can do.
Or should download offline and
I didn't understand.
yeah, okay. Sir.
These examples, if you want, you can do them in
Like
multisim, or you can do it in your notebook. That's up to you.
yeah, okay. Sir.
Okay, then we will meet for the lab session at 2:30.
Thank you, sir.
Thank you, sir.